Expectations are like averages, so now we have an idea about computing those. The next thing we're going to talk about is variance and standard deviation, which is closely related to variance. And this is going to tell us kind of how good the average is at describing what's actually going on. Here are two scenarios. There's an exam. In scenario 1, everybody scores exactly the same, 50%. In scenario 2, half of people score 0 and half of people score 100. The averages are the same in both scenarios. The average of the first scenario is 50. The average of the second scenario, also 50. Let's think about how well these averages describe what's actually going on. So there's an exam and you hear the average is 50. And so you say, okay, I expect that I'm average. I expect that I just barely passed. In the first scenario, your expectation is absolutely correct. It absolutely accords with reality. This is what we call low variance. The average describes the situation very well because everyone's pretty close to average. Now let's think about the second scenario. You hear that the average is 50 and you think, oh gosh, I guess I barely passed. But then you get your score back and actually you got 100%. So this is what we call a high variance. There's a lot of variation. That means that the average doesn't really describe everyone very well. Let's think about putting numbers to this kind of measure of surprise, this measure of how the actual values differ from the average value. Let's talk about the first scenario first. So we have 6 different students. Our average score is 50%. Each student got 50%. So the difference between their score and the expected score is 0. So this is kind of a measure of surprise in some way. How different is each individual test from the average? And what we can do now is we can just average these surprises. For my red student, surprise is 0. For my orange student, surprise is 0. For my yellow student, surprise is 0, and so on. For every single student, the difference between what they expected, the average, and what they actually got is 0. So this is a way that we can start quantifying this idea of variance. Now let's consider the other scenario. The average was 50%, so everyone expects they're getting 50%. This student got 0, and so their kind of surprise factor was 50. The difference between what they expected and what they got was 50. And this is the same for all students. The student got 100. The difference between what she expected and what she got was 50. So again, we can average up these kind of surprise factors. We can average up the difference between the actual score and the average score. So of course, the average of 6 50s is 50. Now there's a little bit of fine print here. This is a calculus class. We want to be able to differentiate and integrate. And absolute value functions are not differentiable everywhere, right? They have that sharp corner. So instead of actually talking about the literal difference, we're going to take the difference and square it. That's going to be something we can differentiate as opposed to an absolute value, which we can't differentiate. So what we're actually going to compute for the variance is the average of my actual value minus my expectation squared. So for the green person, this is my contribution to the variance. For the blue person, this is my contribution to the variance. For the red person, this is my contribution to the variance. For the yellow person, this is my contribution to the variance, and so on. So our variance in this case is actually 50 squared. So 50 is maybe a better representation of what's going on, but we and other people are going to be sort of doing calculus to this computation, and so it's nice if it's differentiable. So that's why we use squared. Here is the definition of variance for a continuous random variable, and let's see how it's really just the same idea as what we did just a second ago. So I'm taking all values from minus infinity to infinity, so every possible value. This is kind of my surprise. This is what actually comes up minus the expectation or average. Then rather than take the absolute value, which is hard to anti-differentiate, I'm going to take the square. So I'm going to just square this. That's going to make sure I don't have to worry about positives and negatives. Now I'm taking this quantity, my kind of surprise squared, and I'm taking the expected value of it, right? I multiply this number by my probability density function, and I integrate over all possible values. So again, we can think of this as the average difference from the average. Now this is the definition of variance. It just so happens that you can compute it a different way as well. So a totally equivalent calculation is I square all my values, take the expectation of that number, take the expectation of my values, and after I've taken it, square it. So I said standard deviation is closely related to variance. In variance, we did this kind of suspicious thing where we just squared everything. That we said that was going to be easier than dealing with the absolute value. But then that gives us kind of silly numbers, like the variance for the test example was 50 squared, but nobody was off by 2,500. So in order to kind of counteract that squaring, the standard deviation is what we get by just taking the square root of the variance.